Welcome back. So last lecture we have seen the definition of dissipativity. The first we defined dissipativity using something called a storage function and a supply rate, right? And essentially it generalizes the concept of energy conservation and dissipation. So if you have a system and if you put in some kind of power input, give some power, basically the internal energy will be growing as much as what is given or less. The difference of these two is typically what we call as dissipation. So that concept is generalized to an abstract, in an abstract fashion, where we have something called a storage function and supply rate, and then just put it bluntly, the storage function, the rate of change of storage function V dot, which we used as a notation, is less than or equal to R of U comma Y, where R is dependent on input and output, typically in a mechanical system that turns out to be power. So essentially the definition of dissipativity is V dot less than or equal to R of U comma Y, right? But then the question that comes to our mind is basically, in order to show something is dissipative, then it seems we require both these elements, the storage function as well as supply rate, right? But then if you actually think about it, the supply rate itself is a property of input and output, and is there a way to somehow figure out some kind of storage function from the system itself? And then we defined briefly about this particular concept of available storage and required supply, and then we showed that they are all nothing but storage function, and every storage function should be somewhere in between these two, right? Some kind of linear combination between these two from a value perspective, right? So that's in a nutshell what we have done last class. And then of course we presented few conditions in terms of how to check a particular system is dissipative or not. They are quite useful in linear systems because we have linear matrix inequalities. In the nonlinear systems they are not that easy, and again we can certainly use sum of squares technique or semi-definite programming for certain classes of nonlinear systems that are represented through perhaps polynomial systems and things like that. So anyway, so that's in a nutshell in terms of what we have done last class. So what we will be doing now is basically try and attempt to solve bunch of problems, right? So here we have this very simple system, x dot equals u with some initial condition, and the output itself is the state, entire state. I mean, scalar systems, that's what we typically have. Need not, sometimes the output could be square of x and things like that, right? Anyway, just for you to know, basically the Laplace transform of this particular system basically is going to be s times x equals u in the zero initial condition case, and therefore the transfer function itself is 1 over s, and we are essentially asking the question that if this particular transfer function 1 over s is positive real. If you recall some of the connections that we have done last class, basically a system is passive if and only if the linear transfer function is positive real if the system is linear, which in this particular case it is. So we could have checked easily the condition for positive realness, but we will look at it purely from a dissipativity perspective. And it says examine the dissipativity of the linear system. It doesn't even say much about which of the dissipativity versions, passivity, what you call non-expansivity and things like that. Okay, so I am going to basically take a guess and then pick this very creative half x square. We always start with half x square. There's nothing so drastically creative about it. It's a very standard thing to do, and we take the derivative of the storage function on the trajectory, right? So that's essentially nothing but x times x dot, which of course is xu. So what we have is v dot is equal to vs dot is equal to xu, and of course this shows that the system G is dissipative with respect to the storage function r of u comma y is given by uy, because x is indeed y, right? But of course, this is what we call as passivity. So this system is passive, right? So that's a good thing to know. In fact, you know, if we had shown VFS is less than or equal to uy, with the derivative v dot is less than or equal to uy, that would have been sufficient. But we are showing that it's actually not just passive; it's actually lossless. Specifically, there is no dissipation whatsoever, right? Now, let's, for the sake of understanding further about this particular system, let us, try to define this available storage function, which, if you recall, is basically supremum, okay, of minus 0 to t u times y dt, right? Take the supply rate, integrate it over from 0 to t for some particular u, and put a minus in front of it, and take supremum. The supremum has to be over all possible inputs, and then of course all positive times. And we know that u is whatever, but y is x. So this is nothing but supremum over all t greater than equal to 0 minus 0 to t u of t, to be specific, and then x of t dt. Okay. Now I could have chosen u to be anything, right? And I'm going to choose something, right? I'm going to choose u to be x dot, right? So assuming that u is x is some function to be determined now, but I'm going to choose u to be in such a way that it's some kind of feedback kind of input, and that's x dot, right? So the supremum, of course, is going to be greater than equal to that particular u, right? X of t, x dot of t dt, right? And this is for all t. I mean, this is true for all t, because if it is true for a specific t, then it's going to be true for all t, right? So, but this is equal to minus half x of square of t between 0 and t, and that will turn out to be half x square of 0 minus minus half x square of t. Okay. So but this one, and then this supremum is greater than or equal to this particular thing, right? And let's go one step further. X of t is what? We have x dot is equal to, sorry, I actually should have chosen u is actually minus, yeah, you should have been chosen minus x dot, and then you would get all the positive things here, and I'm going to get this particular. So choosing u equals minus x dot, that's what I'm doing. I'll get x square of t minus half x 0 square. Okay. So x dot equals minus x. So x dot plus x is 0. So x is e raised to minus t x is 0. Okay. So therefore x of t is e raised to minus t x0, and you can clearly see that basically that could go to 0, or the supreme is at 0 here. There's a simple way. I'm going to probably leave this as a homework problem for you to figure out. One can actually show that v of ax is greater than or equal to half x0 square, right? Somewhere I kind of got lost here, but that's what we will get. But we already know that one of the storage functions is half x square. So therefore we can actually show therefore v of a of x is half x square. Okay, so this is one possibility. Now the question is, can we show then anything else about this? I mean, you know, we kind of tried out one storage function and we showed that it is dissipate with respect to one supply rate. If we wanted to find out if it is say for example r of u comma y is equal to gamma square u square minus u square for some gamma not 0, right? Is this possible, right? So and then we wouldn't have any chance of guessing storage function. One way is actually going back and looking at the available storage kind of ideas. Alternatively, since these are linear systems, perhaps we can actually try a quadratic function, and the most general quadratic function we can think of is in this particular case is ax square, and then see what happens. Okay, vs dot is 2ax x dot, and 2ax x dot is 2a times xu. So what do we know about 2xu? Certainly we know that this is true. 2axu is always less than or equal to a square times x square plus u square. Okay, I'll leave that as homework for you, or for that matter we could even just say a times x square plus u square. Okay, so we seem to be getting somewhere. So we have the form a times u square plus ay square. Okay, but in reality we want minus y square, so it doesn't seem to work out that way. And so therefore we may conclude that this is certainly not, I mean, this is not a concrete proof of showing that this is not dissipative, because we tried one kind of storage function. There's a possibility that all kinds of storage functions are possible. But of course, by knowing linear dissipativity theory, we have seen that basically if and only if certain KYP conditions are satisfied, and we can therefore conclude that this is the best possible storage function, and with which we are unable to pick a such that this is going to be equal to some gamma square u square minus y square. So this is certainly not going to be what we call dissipate with respect to this thing, this kind of supply rate, which we called as non-expansivity. And then I'm going to leave it as a homework for you. Check for any of the input strict passivities. So for example, r of u comma y, check if this is 2 uy minus epsilon 1 u square minus epsilon y square. Is this possibility? Try one of the basically storage functions and then see if you can actually show that it is indeed dissipative with respect to that. So let's now go ahead and then look at one more system. Again, a scalar system for simplicity. Just know that this is equivalent to looking at storage transfer function of 1 over s plus 1 to be positive real, and then we will convince ourselves indeed this is something, one of those things that will be strictly positive real functions, and then therefore we may get slightly more out of this particular example, right? So let's try a x square where a is positive. right? So Vs of x dot therefore is 2ax dot, which is nothing but 2ax times minus x plus u, which is nothing but 2axy minus 2ax square, right? So immediately we know many things, right? So certainly this is less than or equal to 2axy. Sorry, my mistake. This is uy. Okay, so this is certainly passive. Okay, one may be wondering what is this 2a doing or a is doing, and then we can scale the this thing, pick a to be some number that is convenient. But more importantly, if you actually look at this, is nothing but input. Sorry, this is output. This is nothing but minus 2ay square. So this is output strict passive. Okay, so now so this we have a system that is G is output strict passive, therefore it is certainly passive. Okay, we have passivity for free if we have output strict passivity. But we can try to do something more. So we have this 2axu minus 2ay square, right? But we know for sure this is actually less than or equal to, as we have seen earlier, a times x square plus u square minus 2ay square, which is equal to au square minus a y square, right? So which again shows that this is non-expansive with gamma is equal to 1. Okay, non-expansivity is kind of output square is always less than or equal to gamma square u square, and then gamma, if you pick 1, then we can show that this particular system is dissipative with respect to the non-expansive supply rate with gamma equals 1, where you pick a equals 1, right? So you know, one of the things that we have shown earlier is basically such systems which are non-expansive. For example, to start with, when u equals 0, it will be asymptotically stable, whereas in the previous example it's not. 1 over s does not have a pole in the left half plane, open left half plane, but 1 over s plus 1, this particular transfer function has one pole in the open left half plane, so therefore it's automatically asymptotically stable. So we have shown that in multiple ways, right? So and again, one can check for the available supply rate and required supply rate, and then see if they are between ax square kind of a thing, right? So I mean, you seeing through these examples where these are simple enough, therefore we could guess quadratic function and checking it. But in reality, if we want to do a thorough job of actually this is a linear system also, the thorough job of actually verifying something, then we will end up going to these concepts of available supply rate and required supply rates, right? Yeah. So then we will go to a very classical example. So this is a second order system that comes from mechanics. This also fits into some of the electric circuits and things like that, but typically this example, actually the notation and things like that, is coming from mechanical systems, where m is the mass of the inertia, and more generally, and c comes from Coriolis forces and centrifugal forces and things like that, and G is coming from some kind of potential, perhaps gravitational this thing, or some spring. The system is connected to spring and things like that. So what do we know about this particular model? If this happens to be where coming from a mechanical system where there is no dissipation at all, in the sense that no energy gets lost, we will hopefully show that is the case for this particular model through some storage function. So then we know that from the basic mechanics, the time derivative of the inertia minus this 2C matrix, which as I said comes from Coriolis forces and centripetal forces, is a skew symmetric matrix. Recall skew symmetric matrix is basically something that that satisfies H equals minus H transpose. Okay, we'll see in a second. Anyway, so here we chose y equals q. I believe that's a mistake. I think it should be y equals q dot. We will see. And u is the force input, right? And G is coming, typically it's coming from potential energy, and then let's call that potential energy as V of Q. The gradient of that is basically the G of Q is going to enter the basic model. So V is in this particular case a potential energy, and then it's a function of your position Q, and then gradient is what determines, right? So the question here is basically, is this system zero state observable? And then further we can discuss about passivity. What is zero state observability? If we know that if y is 0, and somehow this implies, if y 0 implies the state is going to be 0, then it's called zero state observable, right? So somehow we need to convince ourselves, if q dot is identically 0, okay, of course along with u equals 0, right? If q dot is identically 0, then can we show that somehow g of q means q is actually identically 0. Now if q dot is identically 0, then q double dot is going to be identically 0. So what we end up with, if q dot is identically 0, then we get g of q is 0 identically, right? Now the question is basically, under what conditions does this imply q equals 0, right? So this is true when g of u is going to give a isolated solution, right? So that means basically g of q does not lead to a continuum of solutions. So, and that's not supposed to be assumed here. Actually, v of q has unique local minimum. Okay, so that's a typical assumption about some of these mechanical systems. That should be an additional assumption in this particular case. If the potential energy coming from this particular system, V of Q, has a unique local minimum, then basically around that local minimum, G of Q will have a single solution, and that happens to be Q equals 0, and therefore this particular system is zero state observable under that assumption, right? So now we will consider this particular system. So remember, M the q double dot plus c q dot plus g of q is equal to u, and then y equals q dot is our system. And I'm going to basically consider a storage function which is going to be dependent on both q and q dot, and that's from mechanics I know that it's going to be of the form like this: half q dot transpose m q dot plus v of q, okay, where v of q is the potential energy, right? So if I take the time derivative of this, then I'm going to get so this basically I'm going to get what will I get? So I will get twice of these things. Basically I'll get something like q dot transpose m of q double dot, right? So I'll get twice of that, so I don't need half anymore, plus q dot transpose m dot of q dot plus v prime t q dot, right? Gradient of v with respect to q times the time derivative of q, which will give you q dot, right? So when I substitute for mq double dot, I'm going to get q dot transpose times minus cq dot minus g of q minus plus u plus q dot transpose m dot q dot, and this, remember, this is nothing but g of q, and then therefore I can, this is the transpose, q dot transpose g of q. Okay, so when I rewrite this, q dot transpose g of q will cancel with this. I'll have a q dot transpose, which is y transpose, so I'll have y transpose u, that's coming from this. This is cancelled, this and this will get cancelled, and I'm going to get, of course, plus q dot transpose m dot minus c times q dot, right? So this is the term that's a problem. Otherwise we could have concluded passivity v dot s is equal to y transpose u, passivity and lossless, right? But we know that this is a skew symmetric matrix. Remember, d by dt of m minus c is skew symmetric. Now let's actually understand skew symmetry very well. So I have x equals minus hx transpose. So I'm going to take some real vector and then multiply on both sides, x transpose hx, which is same thing as minus x transpose h transpose x, and then I can transpose this particular quantity, which is nothing but minus x transpose h times x. Okay, so I have this quantity is equal to minus of that, therefore that has to be equal to 0. So this is an amazing property that skew symmetric matrices satisfy, which is basically take any skew symmetric matrix and then you multiply with some real vector on both sides, then it will produce a 0. And if you are not convinced, but let's actually take a very simple 2 by 2 matrix, 0 1 minus 1 0, and x to be, I don't know, AB. So x transpose hx is going to be AB times 0 1 minus 1 1 0 times AB, which is minus b a times AB, which is going to be 0. So nothing surprising. So essentially what we showed, that is basically this part is going to go to 0, and therefore we will be left with vs dot is equal to u transpose y, which implies that the system is passive, right? So can it be strictly passive? The answer is no, right? If we want strict passivity, basically typically in mechanical systems, in addition to this component coming from Coriolis forces and centrifugal forces, you also have damping. This damping will provide, the damping is probably a positive definite matrix, and that will give us the essential damping. So that will lead us to strict passivity, and also we can actually show non-expansivity and things like that. But let's go further a little bit and then say, if I chose u to be minus some d times x, then one can actually show that this system is Lyapunov stable. Okay, I'm going to leave that as a homework problem. Show for d greater than equal to 0, if u equals dx, then the closed loop system is Lyapunov stable, in the sense that the zero equilibrium is Lyapunov stable. But actually much more, because of the zero state observability, we can show that this is indeed asymptotically stable. Okay, asymptotic from zero state observability. Remember, the zero state observability could be proved only because of the fact that we assume that this G of Q has one single equilibrium isolated fixed point, right? So otherwise we wouldn't have asymptotic stability. We would end up with something more complex than that. Okay, so let's see one more system, which is again second order system, scalar system written as actually a state space, and they all have common properties. So let's try in this particular case something like half x1 square plus, I don't know, we can scale the second one, alpha to square. This is not the most general quadratic, but we can try. Okay, and then vs x dot is going to be equal to x1 x1 dot plus alpha x2 dot, which is nothing but x1 x2 plus minus alpha a x2 sine of x1 minus alpha ab x2 square plus alpha x2u, right? So I can rearrange these terms in such a way that x1 x2 times x1 minus alpha a sine x1, okay, and minus alpha ab x2 square plus alpha uy, right? So alpha is up for grabs still. So now can we say something about this part? Okay, certainly locally we can say that by picking alpha to be 1 over a, here a is assumed to be positive, let's say. A and B are positive. Did I say that? Actually, I should have said A, B are positive here. So if A is positive, alpha can be picked to be 1 over A, and then basically close enough to 0. Basically, we can show that something is true about this, and this part is anyway negative, and then alpha uy. So perhaps we can show this is nothing but alpha uy, right? And showing passivity. Okay, so but it's easier said than done. Is this negative? Well, sorry, sine of x1 is if you recall, sine of x1 is approximately x1 minus x1 cube by 3 plus higher order terms, right? So we can actually substitute that here and we'll get a positive number, and then we'll end up with basically difficulty of showing passivity, right? So therefore, though we picked some storage function, we are unable to show passivity. So instead we could actually consider something like 1 minus cosine of x1 plus half x2 square. Again, you can scale it with alpha, and then vs dot is going to be equal to sine of x1 times x1 dot plus alpha x2 dot, which is going to give me x2 times sine of x1 plus alpha x2 times minus a sine x1 minus alpha b x2 square plus alpha times x2u. Okay, so the nice thing is now I pick alpha is equal to 1 over a and cancel out the sine terms, and I'm going to get this is equal to alpha is 1 over a, so minus b by a x2 square plus 1 over a x2u, and writing this in terms of output, I'm going to get minus 1 over a uy minus b by a y square, right? So this shows output strict passivity, right? So output strict passivity, And we can actually show non-expansivity also. I mean, output strict passivity implies passivity, and this also implies, we have done this a couple of times by showing uy is less than equal to y square plus u square, half of that, and then basically by manipulating one can show even non-expansivity, right? So and then I'm going to leave it up to you under what conditions this particular system is actually non-expansive, and therefore we can show basically under u equals 0 this is going to be asymptotically stable. Through non-expansivity or even strict passivity we can show Lyapunov stability again. Let's explore if this is indeed zero state observable. What is zero state observable? If x2 is 0, we should be able to show both x1 and x2 are 0. Of course, x2 is 0 implies x2 is 0 anyway, that's an obvious thing. But if x2 is 0, x dot is 0, right? So this part is 0, u is 0. So we'll get sign of x1 is 0. So therefore we'll have multiple possibilities. X1 dot is also going to be 0, shows that basically sign of x1 will be at a constant. But locally, therefore x1 equals 0, locally if you don't go too far from the x1 equals 0, x2 equals 0 point, then basically this system is actually zero state observable in a region around the origin, and then that is helpful to show that this system is indeed asymptotically stable. The zero equilibrium is asymptotically stable with u equals 0. So therefore you could pick u equals 0 to be your stabilizing controller, right? Okay, so that ends this particular lecture. This is essentially few examples where we saw how to show dissipativity by guessing storage function. In case we cannot guess storage function, then basically we'll have to end up using the concepts of VA and things like that in all these systems, even though the last one is truly nonlinear, but we had to guess the storage function in terms of cosine and things like that, and then showed, right? So hopefully it gives you some understanding of definition of dissipativity. We will now utilize the concept of dissipativity in one of the most important ways of controlling systems, right? So we will then next lecture we will look at basically feedback interconnection of dissipative systems. Thank you.